Another very interesting topic in nuclear physics is the next video on the biological effects of radiation. And what we're going to do here, which will be a surprise to a lot of people, I think, is the effect of self-radiation. It turns out that yes, we are exposed to radiation all the time. Some comes from the Earth, bubbles up from the Earth, and we're exposed to that radiation. Sometimes we live in an environment where there is additional radiation because of nuclear power plants or other things that are going on. Maybe we live close to a uranium mine or something like that. Or sometimes, or not sometimes, but all the time, we get radiation from space. So we're constantly being bombarded by radiation. But what a lot of people don't realize, we're also being bombarded by our self-radiation, because within our own body we have radioactive isotopes. For example, we have carbon-14 in our body, and that's constantly decaying and constantly spewing out beta particles, and so therefore we're constantly being exposed to radiation from our own bodies. Kind of wonder how much radiation we're exposed to. Let's try to figure that out. So what we're trying to do here is calculate the equivalent dose per year that we receive from our own bodies due to carbon-14 decay. Now it turns out there's other kinds of decays in our body as well, but just let's concentrate on carbon-14. So let's take a typical person with a mass of 75 kilograms, which is maybe 170 pounds. And 18% of your body typically is carbon. And of that 18%, if we compare the amount of carbon-14 in our bodies compared to the total carbon in our bodies, it's about 1 in a trillion, or 1.33 in a trillion. So for every trillion carbon atoms in our body, one of them is a carbon-14. You say, 1 in a trillion, do I need to worry? Well, let's find out. Also, what you need to know is that each time a single carbon-14 decays into nitrogen, it releases 0.156 MeVs, million electron volts of energy. So, how much exposure do we have from our own bodies? Let's figure it out. Well, first of all, we need to find the decay rate. What is the rate of decay? And of course, the rate of decay is the change of the radioactive particles, and we're talking about of course, the radioactive particles divided by time, and that's typically the decay constant times the total number of carbon-14 particles. Okay, so what we have to do is find out how many carbon-14 particles we have and what the decay constant is of those carbon-14 particles. So starting out with the number of particles, the number of carbon-14 particles is equal to, well, let's see here. We start off with a mass of 75 kilograms. And of that, 18% is carbon, so 0.18 is carbon. And of that carbon, we only have this many carbon-14 atoms. So the ratio is 1.33 times 10 to the minus 12 carbon-14 atoms. So what we have now with this is the mass of carbon-14 atoms in our bodies. So we have the mass in kilograms. So to find it, so we have to convert that to number of atoms. So let's find the mass in grams. So we have 1,000 grams per kilogram. And then, of course, to go to the number of carbon-14 atoms, we have to convert from grams to moles. And so 1 mole is equal to 12 grams. Oh no, I can't use 12, I need to use 14 because carbon-14 is 14 grams per mole, so 14 grams per mole. And then we have to convert to number of atoms, so number of atoms per mole. And of course the number of atoms can be expressed as Avogadro's number, or 6.022 times 10 to the 23 atoms. So what we've done now is we've taken the mass and converted to number of carbon-14 atoms in a person's body if that person has a mass of 75 kilograms. So with the calculator, let's find out how many carbon-14 atoms in a typical person. So we have 75 times 0.18 times 1.33 e to the 12th minus. So that's the total number of kilograms of carbon-14. Convert that to grams, multiply times 1,000. Then we convert to moles divided by 14, and then we convert it to number of atoms is times 6.022 e to the 23 equals, and so we have in our bodies typically 7.72 times 10 to the 14th carbon-14 atoms. I got to be careful here with the 14s, carbon-14 atoms in our bodies. All right, next. I need to find the decay rate, the And for that, I need to find the decay constant. So the decay constant is equal to 0.693 divided by the half-life of the radioactive material. For carbon-14, that's 5,730 years. So this is 0.693 divided by 5,730 years. And of course, we want to convert that to seconds. So multiply this times 365 days per year, and then multiply it times 86,400 seconds per day. And that will give us the decay constant of carbon-14. So 5730 times 365 times 86,400, that goes in the denominator, take the inverse of that, and multiply it times 0.693 equals, and that gives us 3.84 times 10 to the minus 12, and that would be decays per second, right? So that would be decays per second. That's the decay rate. If I multiply those two numbers together, I get the decay rate of the amount of carbon-14 in our bodies. So the rate of decay is equal to decay constant, 3.84 times 10 to the minus 12, that's decays per second, times the number of atoms that we have in our bodies that are radioactive, 7.72 times 10 to the 14th, at least that's carbon-14 atoms. So we multiply those two together, so times 7.72 e to the 14th equals 2,960. 2,960 decays per second. So now, typical person, every second, 2,960 carbon-14 atoms in our body decay and spew out an alpha particle, spew out an electron that goes ripping through our bodies, causing damage. Is that significant? Well, if each decay gives us this much energy, so that means the energy per second is equal to 2,960 decays per second, and multiply that times 0.156 MeVs per decay. That tells us how much energy per second that we get. So we take that number, 2960, and multiply it times 0.156 equals, and that gives us 462 MeVs per second of energy imparted in our bodies by that decay. Let's now convert that to joules. So we have, well, first of all, let's convert it to EV. So EV per MeV, and there's a million per MeV, and then we want to convert that to joules, joules per electron volt, and it's 1.6 times 10 to the minus 19. So first of all, we're going to take that number and multiply times a million, so times 1 e to the 6th, and then multiply times 1.6 e to the 19 minus, so we've converted that to joules, and so this is equal to 7.4 times 10 to the minus 11 joules per second. Okay, so now going back to our basic units of equivalent dose. The dose that we receive. So received dose, the received dose is 7.4 times 10 to the minus 11 joules per second. And that would be in terms of grays, so that would be 7.4 times 10 to the minus 11 grays per second. Let me do it like that, grays per second. All right, now what is the effective dose or the equivalent dose? About the equivalent dose. So the equivalent dose is the dose that we received, which is the grays per second. So it would be the received dose, the dose received, and multiplied times the RBE. So what is the RBE in this case? Well, these are electrons, and electrons have an RBE between 1 and 2. So let's take the average of 1.5. So this is equal to 7.4 times 10 to the minus 11, and multiply the whole thing times 1.5. And of course, when we multiply times the RBE, we no longer talk about grays, but we now talk about sieverts. So this would be SV or sieverts. So multiply this times 1.5, we get 1.1 times 10 to the minus 10 sieverts. 1.1 times 10 to the minus 10 sieverts, and that is, of course, per second. If we now want to calculate how much is the equivalent dose per year, because that's usually what they do, is how much dose do you receive over a period of a year, we have to multiply it times the number of seconds in a year. So if we multiply this times 86,400 seconds per day, and then multiply that times 365 days per year, we now have the equivalent dose per year. All right, so times 86,400 and times 365, and now we are at 3.5, so this is equal to 3.5 millisieverts per year. So, all right, I am back. I just looked at my notes, and there's a couple things I just realized. One of them is that this was the total energy received per year in sieverts for the whole body, but the basic units of a sievert is the energy received per kilogram, and since that energy is spread out over a body that has a mass of 75 kilograms, we actually have to divide that number by 75. So the equivalent dose, this is total. This would be the total equivalent dose. And then if we want to convert that to the dose per kilogram, since the person has a mass of 75 kilograms, then let me put a little box over here and continue with this number right here. So the equivalent dose per kilogram, I have to take this amount, so this is equal to 3.5 millisievert per year, and multiply times 1 over 75 kilograms. So now I have converted the dose, the equivalent dose, in a per kilogram basis. So divide that by 75, and now we have a much smaller number. So this is equal to 47 microsieverts. This would be sieverts, microsieverts per year. Now that is a very small amount compared to what we normally receive in a given year. It turned out when I first saw this number, I was a little bit confused. I go, wow, that seems like a little bit high. I had forgotten to divide it by 75. But in addition to that, I realized also that the yearly exposure due to natural causes is about 4 millisieverts per year per kilogram. And so 47 microsieverts divided by 4 millisieverts is a little bit over percent. It's about 1.25%, 1.25% of what you normally receive in a year through natural exposure. So at first I may have alarmed you saying, oh, we have carbon-14 in our bodies, it decays, that gives us radiation. But it turns out compared to what we receive from other sources around us, it's only a little bit over 1%. So again, the way you do that is you figure out how much energy you receive per decay. You have to understand how many atoms you have in your body that are decaying and what the decay constant is. If you multiply those two together, you will get the number of decays per second, each giving you this much energy. So then you calculate the total amount of energy that you get per second, because this is a number of decays per second. You multiply the times the right things to get the decays per year, and also if you convert to joules, then you get, of course, the right conversion units. You multiply that times the seconds per day and the days per year to get it in terms of energy received per year. Of course, we have to divide by 75 kilograms because it's over the whole body. That gives you the yearly amount of equivalent dose that you received, which is the energy received multiplied, of course, times the RBE of electrons, which is about 1.5. Okay, and that's how you calculate the biological effects of radiation. So I have another example where we're going to look at the biological effects of radiation given to us through a medical procedure, and we'll see how that works in just a moment.